What we're going to do now is to get you to the point where you can calculate more or less everything everywhere in a simple transmission line situation. So if you were given the basic parameters of your generator, your source impedance, and then the transmission line characteristic Z0 and the load, that you should be able to calculate the current, the voltage, which you should be able to do from the previous discussion, but I also want us to get to the point where we can calculate the power everywhere. Where we're going with these power calculations is next up we're going to talk about different termination schemes that will be able to minimize or eliminate the reflections. However, to understand all of the trade-offs, we also have to be able to see where all the power goes. And so the main goal that we want to be able to get to is not only to find the current and the voltage at every location and any time, but also to be able to find the power at any location at any time, and more importantly, be able to find the power that's being dissipated at the load end and the power that's being dissipated on the generator side. And the key equation that we're going to use and turn back to is the fact that the power is equal to the product of the current and the voltage. And so to get there first, we're just going to go through the exercise to solve for the current and the voltage, again, at all locations and at all times. And so this is actually a good review of what we talked about previously as well. So the first thing we want to do is we want to calculate the key parameters that we need to track the voltage and the current. So that's the input voltage, which is the voltage divider between VG divided between ZG and Z0, and also gamma G and gamma L, where Vn is the voltage divider between Z0, ZG plus Z0, and gamma, I'll just combine gamma generator, gamma load is equal to new, which in this case generator load, minus old, which is a transmission line, and the sum of the two, so ZG or ZL plus Z0. Once we have that, we want to find all of the voltages, so V plus, V minus, V plus plus, V minus minus, and so this is going to be Vn. This is V plus times gamma on the load side. This is the reflection off of the generator, so the negative wave, and then multiplied by the reflection coefficient of the generator, and so on and so forth. This is V plus plus times gamma load. So let's just visualize where that is in this picture. So over here we'll be able to calculate, this is your initial wave going in, and then it bounces off, so then you have this reflection, and then you have the reflection off the generator, and then that bounces off the load side. Now separately, you also, once you have all these voltages, you will also be able to find the currents. So remember, the currents, the trick is that for positive waves, it's just divided by the characteristic impedance of the line. So, but for a negative going wave, you have to remember to add in a negative sign. So negative V minus Z0. And then the reflected wave off of that is going to be, again, positive. So this V plus plus that you found over here, divided by Z0, and then I minus minus is, again, don't forget the negative sign, or what? Or I will cry when I see it. That's right. Divided by Z0. So let's just label that over here. This is just notation that I use just to put all of the basic information on here visually. So what I do is I usually put the corresponding currents that I find in parentheses. Then plus plus, I minus minus, And then quite often I'll also just have the needed reflection coefficients over here when you bounce off so that you can see. The next thing we want to do is we've calculated these are basically the change in voltage or current, which I like to think of as the change in elevation. So we want to go ahead and start with the actual elevations of each of these triangle slices. So again, I'm kind of telling you how far up or down this goes into or out of the page. And so at the start here, this value, I usually circle this so that it represents what the value of the triangle is. And so this V0 is going to be equal to 0 because it hasn't really seen the initial incoming wave yet. But next up, as you cross over across this line over here, now this triangle slice is going to be value V1, where V1 is going to be equal to V plus, right? You cross this threshold, so now you have this value, that's V1. And let's go ahead and just calculate the currents too. So I0 is also going to be 0, and then there's a corresponding I1 that's going to be equal to I plus. I'm just gonna squeeze that in there, I0. Then we're gonna circle this V1, and then it has a corresponding I1. And then again, that's equal to V plus and I plus respectively. And then next up, you cross this threshold, which changes your elevation by V minus or I minus. So then you get a V2 and a corresponding I2, where if we go back and look, V2 is going to be equal to the value before this, the value of this slice, but then this change in elevation. So it's going to be V1 plus V minus. And then similarly with the I, you have I2 is going to be equal to I1 plus I minus. And then we just play this game over and over. So next up we have V3, I3, and V4 with a corresponding I4. And we go back and look. You get V3 by crossing over to this value. So V3 is going to be equal to V2 plus V plus plus. And similarly, I3 is going to be equal to I2 plus I plus plus. And then if we want to go one more, we have V4 is going to be equal to V3 plus, and then you cross over that threshold, so your elevation changes by V minus minus. And I4 is going to be equal to, I4 is in turn going to be equal to I3 plus I minus minus. So these are all values that you just have to add and add up and track as you go along. But don't forget, next up, we are also interested in what the voltage and the current is at the load and the generator. So we also want to be able to track what the voltage and currents are at the load and the generator. Let's do the load first. So the load, the values at the load are going to change. You're going to have one value from 0 to t, and another value from t to 3t, and then another value from 3t to 5t. So from t equals 0 to t equals t to 3t, and t equals 3t to 5t, which we don't really get to. We would have to go a lot further down. But at t equals 0, we see that the voltage and current at the load is equal to 0. So VL is equal to 0, IL is equal to 0. From t to 3t, this chunk here, you see you cross this threshold and this threshold. So VL is going to be equal to V plus plus V minus. You cross this threshold and this threshold, which is actually equal to V2. So it's actually a value that we had before. We can just copy it over. And then similarly, IL is going to be equal to I2. And then from 3t to 5t, you can see you cross this line and cross this line. So you take the previous result, you add V++, and you add V minus minus. And if you look back at all the values we found, that's basically V4. So in that range, VL is going to be equal to V4, and IL is going to be equal to I4. And then finally, this is at the load. And then the last part is at the generator side. So if we look at the generator side, there's one value from 0 to 2t, and then one value from 2t to 4t. So from t goes from 0 to 2t, we have something going on, and t equals 2t to 4t, we have some stuff going on. So from 0 to 2t, at t equals 0, this wave goes, this V plus wave already goes out. So you can see that the voltage at the generator is going to be equal to V plus, right? Or in other words, if we use the same logic as before, it's V1, right? Or V plus, depending on which one you want. And IG at this stage is going to be equal to I1. And then next up, once you get to this range here and here, you cross this V minus and this V plus plus threshold. So the answer is your prior answer, V plus V minus plus V plus plus, which is going to be equal to V3 when you think about what V3 is. So VG is going to be equal to V3, and IG is going to be equal to I3. And so now you have the voltages and the currents at anywhere in this range, including at the generator as well as at the load. And now the last step is to simply calculate the power. So now, because you already did all the hard work laying out the foundation of all of these numbers, being able to find the power anywhere would just be simply taking the respective current and multiply it by the respective voltage. So you use P equals IV. Or in other words, if you want to find the power at the load at any point in time, you just take your IL times VL that you had calculated over here, and if you wanted the power dissipated at the generator, you just take the current at the generator and the voltage at the generator for the time period that you're interested in, or if you were asked to plot it, you would just set it at the product of these two for t equals 0 to 2t, and then between 2t and 4t, it would be the product of these two. And then, or the other thing is if you say wanted to find the power dissipated from this reflected wave, the power at the first reflection, then that would simply be I minus V minus. So if you were to ask, how much power was at the load versus how much power was reflected, you would use this formula to find the power at the load, and then at the first reflection, if that was what you were asking, you would use that to find the power dissipated. So there's a lot of math, but really it's addition and subtraction. The main tricky part that you have to be careful is that when you're calculating negative currents, remember you take the voltage value and don't forget to add a negative sign after you divide it by the characteristic impedance of the transmission line Z0. So again, once you have these negative signs and you didn't forget them, the rest is just a matter of bookkeeping and adding the correct values. And I think that being able to visualize it in this plot and drawing them using this notation makes sure that you have ensures that you have the right numbers corresponding to the right thing. And again, once you have all the voltages and all the currents across this two-dimensional space, plus the generator and the load, it's just a matter of multiplying the two together. Easy peasy.